All right, so let's just dive right in and look at this first example. So here we have the sum of two rational functions. And I can integrate those functions just by splitting it into two parts, right? So I could write that this is equal to the integral of, and I'll put the 2 out front, 2, right? And then this is just becomes 1 over x minus 1 dx, all right? And then plus the integral of 1 over x plus 3 dx. Okay, now this is fairly straightforward. I could do a substitution here. I usually don't bother because I know I've done enough of these, I guess, but I'll do a substitution on this one. So if I let u equal x minus 1, right, then du is just equal to dx, right, because there's no coefficient, and that constant, when I differentiate it, just becomes 0. So what I end up with is the integral of 1 over u du, right, which is just the natural log of the absolute value of u. Okay, now whenever I have a x plus a constant, right, with no coefficient, I usually just go straight to writing this becomes 2 times the natural log of the absolute value of x minus 1, right? And the same thing happens over here. I could do a substitution and say u is equal to x plus 3, so du is dx, but I'll just end up with the natural log of x plus 3 and then plus c. Okay, so that's fairly straightforward. But let's take a look at this next one. This next one looks a lot more complicated, but it's actually the same problem. So if I were to, you'll see that pretty easily if I take these two fractions, these two rational functions, and I combine them. So if I take 2 over x minus 1, whoops, and plus 1 over x plus 3, I can combine them if they have a common denominator, right? So I'm going to multiply this one times x minus 1 over x minus 1, right? And then I can multiply this by x plus 3 over x plus 3. Okay, and I multiply that out, I'll get 2x plus 6 in the numerator, and then plus x minus 1. And all of that will be over this common denominator of x minus 1 times x plus 3. All right, so, and then I can combine these terms in the numerator. I'll end up with 3x plus 5 over x minus 1 times x plus 3. And if I were to multiply the denominator out, I would end up with x squared, and then I have minus 1x plus 3x, which becomes 2x, and then minus 1 times 3 becomes minus 3. So you can see it's the same, right? This matches, so it's the same problem. Now, but the question is, how would I know that if I was given a problem in this form to start out with, this form in example 2? How would I know that that's the same thing? And that's the motivating question behind partial fractions, is to take a rational function and break it down into the sum of simpler rational functions, okay? And that's what I'm going to show you how to do in this example 2. How can I take this 3x plus 5 over x squared plus 2x minus 3 and break it down? So the first thing I would do is just factor the denominator so that you can see what's happening. So if I factor the denominator, you can see that, the factors of -3 that add up to 2, that would give me x, oops, not plus, x minus 1 times x plus 3, right? And the idea here is to then take this rational function and write it in the form that we'd like to get it in, right? Because I know I could, if I have, I could take two rational functions with these two denominators, right? Something over x minus 1 plus something over x plus 3, right? That's the form I would like to get it in, because those denominators are could be combined into a fraction that has this denominator here in the original function. So, and then it's just a matter of figuring out, okay, what is a and what is b? So once we get the denominator factored, and then we set it equal to what we would like to see, what we want to do next is clear the fractions, or clear the denominators of the fractions, right? We want to make these into a little bit simpler to deal with. So what I'm going to do here, I'm just going to multiply both sides by x minus 1 times x plus 3. Okay, both sides, all of both sides. I'm going to multiply by x minus 1 times x minus 3. Okay, now over here this is going to completely cancel, and I'll end up with 3x plus 5. And then I can distribute the x minus 1 times x, oops, this should be x plus 3. And when I multiply that by the first term, the x minus 1s will cancel, and I end up with a times x plus 3. And when I multiply this product times the second term, I'll end up with b, and then the x plus 3s will cancel, so I end up with b times x minus 1. Okay. And then what I'm going to do, and I could like rearrange this and probably get a system of equations in terms of a and b, but it's actually easier. There's a kind of a sneaky trick to this. What I'm going to do is choose convenient values of x. Okay, so for example, if I say let's let x equal 1, okay, what happens? I have 3 times 1, I'm just replacing x with 1, plus 5, right? That's the left-hand side of the equation. And then I have a times 1 plus 3. And you can see that this second term just becomes 0, because 1 minus 1, so b times 1 minus 1 just becomes 0, right? So that's 0. And that allows me to solve for a, okay? And that's actually why I chose x equal 1, because it makes that second term go away, right? Because 1 minus 1 is 0. So that's why I chose that as a convenient value. So this side then becomes 8, and this side becomes 4a. And so you can see that a has to be equal to 2. Okay? So we have a. All right, good. Now let's choose another convenient value. Another convenient value would be x equals minus 3. And that's because, so I'm just looking at these terms. What's going to make the a term go away so I can solve for b? If I put in x equals negative 3, then this first term goes away, and all I have left is b. So we'll end up with 3 times minus 3 plus 5 equals, I'll just go ahead and write it all out. We'll have a minus 3 plus 3, which will go away. And then we'll have b times minus 3 minus 1. Okay, so here we have negative 9 plus 5, so this becomes a negative 4. And on the other side, we're just going to have negative 4 times b. So that's telling us that b is equal to 1. All right, so we have a and b. Let me scroll down here a little bit so I can get some more room. We have a and b, and now we can write our partial fraction decomposition. So we're taking this probably scroll back up here. We're taking this original rational function and breaking it into two parts. So we end up with, and I could even write it as an integral, right? Because I'm trying to solve the integral. So I will get 2 over x minus 1 plus 1 over x plus 3, okay, dx. And I already did that, right? I did that in example 1. So that's the motivating question here. This is the idea behind the method of partial fractions, is to take a a more complicated rational function and break it down into something that's easier to integrate. So so that we can again, we're finding techniques to integrate, and the method of partial fractions can help you do that.